Welcome back. Today we're talking about section 2.2 power functions, and our objectives for this section are these. I'd be able to identify a power function, be able to pick out the parts of a power function, be able to look at the graph of a power function and determine domain and range, look at its attributes, pick it apart, and then see how power functions in general operate in relationship to one another. So let's go. First of all, a power function looks like this. F of x is equal to k times x to the a power. So we've got a, so x to some power. K is called our constant of variation. And a is our power. K and a are non-zero constants. Okay, so they can't be zero, but as we operate in this, you're going to see they could be a fraction, they could be negative, they could be positive. Here are some examples. Circumference. When we talk about circumference, circumference is equal to 2 pi times radius. Okay, the power is 1 and the constant of variation is 2 pi. Okay, because radius is what is varying, and then so our constant of variation is the constants that are being multiplied by it. Another example is area of a circle. And what you're going to see with this is you start to see this pattern. Pi times radius squared. In this case, if I'm thinking about it in terms of a power function, I'm looking for the constant of variation, meaning a number times something to some power. Okay? And that something, the x in our original, or the radius in our circumference equation, is what is dependent in the problem. So in this case, it's I need the radius of the circle to be able to calculate it. So my power is 2, and my constant of variation in this case is just pi. Another one is the force of gravity. Force of gravity is F is equal to K divided by D squared. In this case, my power is -2 because my distance is on the bottom, and if it's on the bottom of a fraction, that means it has a negative exponent. My constant of variation is K. So this would essentially be K times D to the -2 power. Okay, so force is inversely proportional to the distance from the center of the Earth. Boyle's law looks like this. V equals K over P. Okay, and so in this case, it is K times P to the -1 power. And so my power is -1, and my constant is K. All right? So it's recognizing situations where we can write it as some number I know times something I'm varying. So that's my exponent, or my variable, sorry, like an x or a radius or a pressure in terms of Boyle's law, or a distance in terms of the gravitational pull. And being able to rewrite it so that it's my constant times my variable to a power, whether that's positive or negative. Direct variation is power functions with positive powers, okay? Indirect variations are functions with negative powers. So these are going to have multiplication in them. And these are going to be written, they can be written as multiplication to a negative power, but generally they're going to have division in them. Okay? Sometimes the trickiest part about power functions is understanding where they're present, because the wording is tricky. And so understanding what the wording is saying helps us to understand, am I actually dealing with the power function? For example, the volume V of a circular cylinder with a fixed height is proportional to the square of its radius. Proportional to. Okay, so when I'm talking about proportional to, I'm talking about direct variations. Okay, so positive power. And so volume is directly proportional to square, so the square of the radius. So directly proportional to means K is some constant, okay, and it's times radius squared because that's what's directly proportional to. The volume is directly proportional to boom, boom. Okay, so if I see the word proportional to, that clues me in it's a power function. That tells me it's multiplication. Okay. Another way to say this would be the speed of the current in a whirlpool varies inversely. Inversely tells me negative power or division. And the speed in a whirlpool varies inversely with the distance from the whirlpool center. So that tells me that I have d to a negative power, so speed equals k times d to the minus 1. Inverse proportionality, okay? So inverse relationship implies that there is this negative power on my distance, okay? And so when we start to look at these graphs, here's what we're doing. We're taking a function and we're saying, okay, is this a power function? If so, tell me the power. And when you can tell me the power, then you can start to analyze the graph. So in this case, let's rewrite. Because I want it to be f of x is equal to k times x to some power. K can be 1, k could be more than 1, but at the very least we need to be able to write it as x to a power. Well, in this case, f of x is equal to x to the 1/3 power. Okay, and so if I'm talking about power and constant variation, my power is 1/3. My constant of variation, well, what would it be? It's the constant out front. Well, in this case, it's a 1. When I graph this, and you can graph this on your graphing calculator. I'm going to grab mine from over here. Okay, graphing calculator. I'm going to graph either the cube root or x to the 1/3 power. Looks like this. It's not a coincidence that it looks like an x cubed on its side because it's x to the 1/3, but we'll discuss that at some other point. My domain, so that's what can't go in. Well, in this case, my x, everything can go in. Don't be confused. This is a cube root. This is not a square root. Okay, if this was a square root, it has to be positive, but because it's a cube root, my domain is -infinity to infinity. How do I know that? Well, look at my x values. For every x value, as I go along, I have a y value, so the graph is there. My range, these would keep going down into -infinity and to positive infinity, so -infinity to positive infinity. Is it continuous? Yes. A reminder, continuity means, could I draw that without picking up my pencil? Yes, I certainly could. Increasing and decreasing behavior, meaning, is it going up and to the right? Is it going down and to the right? Is it remaining constant? Well, check it out. Everywhere I go, as I draw, as I move to the right, I'm going up. So it's increasing on domain, meaning every part is going up and to the right. But Mr. Seris, this is going down and to the left. I'm talking about as I move to the right. Is it going up or down? Symmetry. This one's interesting. Okay, so symmetry, is it x-axis symmetry? No. Is it y-axis symmetry? No. Is it origin symmetry? Meaning, is it over y and then over x, or over x and over y? Yes. So my symmetry in this case is origin symmetry, which means it is an odd function. We talked about these things last chapter. Okay, boundedness. Does it have a boundary up here or below that the graph can't get past? Like, is it coming to y equals 5 and it won't get there? No, it's going to keep increasing. So if a function's always increasing, it's not bounded. Okay, it's not bounded if it's not bounded above if it keeps increasing. Well, if this keeps decreasing down this way, it's not bounded below either. So this is not bounded. Local extrema, none. This is not a case where I have, hills or valleys, okay? This just continues to go up and down. How am I going to know if I have local extrema? Well, you're going to have a part that's increasing, and then a part that's decreasing, and then a part that's increasing, and then a part that's decreasing. That change, where it goes from increasing to decreasing, that's going to tell you I have a maxima. If it goes from decreasing to increasing, that's where you know you're going to have a minima. Asymptotes, none. Here's something interesting, end behavior. We're going to talk about this more and more and more. But what I'm talking about is my limits. And you're probably like, well, I don't really know what that is. You have to think about the ends, okay? So there's two of them. So we're going to have two limits, one for the right end, one for the left end. As the right end goes to infinity, so that's what we're saying here. Check this out. The limit as x goes to infinity, okay? The other one is the limit as x goes to negative infinity, okay? Check this out. So as x goes to infinity, meaning the numbers in x get increasingly big, what is my graph doing? Where's it going? Is it headed down to 0? Is it headed to negative infinity? Is it headed to positive infinity? And so in this case, my limit as x goes to infinity of the cube root of x is equal to infinity. Because as the right side, so this is the right side. This is the left. As the right side goes on, goes to infinity. As the left side goes on, where is it going? So the limit as the cube root of x goes to negative infinity. So as x goes into negative infinity, what's it doing? Well, it's going to negative infinity. Okay, you're going to need to be able to do this so well and analyze a graph so well. Okay, let's do one more. If g of x is 1 over x squared, I can rewrite g of x like this. So g of x is equal to k times x to the negative 2 power. Well, in this case, my power is negative 2, my constant of variation. I put a k out front because that's my constant. Well, what has to go there in this case? Well, in this case, this is 1, so my constant of variation is 1. If I graph this, looks like this. Okay, my graph looks like this. And so my domain, notice what's happening here. I have to figure out where are the parts that are going to be a problem. Well, when you look at this, what cannot go in? And hopefully you're saying 0, Mr. Seris, 0 can't go in. But everything else can. So it goes from negative infinity to 0, and then 0 is excluded. Well, how could I possibly know that by looking at the graph? Look at where the asymptote is. It's going to get infinitely close to 0 but never touch it on both sides. So 0 is an asymptote. My range. What could possibly come out? Well, when I look at my graph, check out what's happening here. Infinitely big values of y. But at the bottom, I'm not going into the negative part. I'm not going into y equals negative 1 or y equals negative 2. In fact, I have this graph that kind of flattens out right when it gets to the x-axis. And so my range is all the way up to infinity, but it stops at 0, but 0 is not included because there's this asymptote right here. Okay? How would I know that? Well, horizontal asymptote, Bobo, Betsy, Botu, right? Bigger on bottom. So y equals 0 is an asymptote. Continuity? No. It's not continuous. How do I know? Well, I had to pick up my pencil. So when I was drawing this, I had to draw it to go into infinity, pick up my pencil, hop over, and then draw my next part. And so what kind of discontinuity is it? It's an infinite discontinuity. How do I know that? Well, the point where I had to pick up my pencil was headed to infinity and beyond. And then I had to draw the other side, which came from infinity and beyond. Increasing and decreasing behavior. As I move to the right, so continuity can help us with this. As I move to the right, so let's look at this left-hand part of the graph. As I move to the right, am I going up or down? Yeah, I'm going up. So it's increasing from negative infinity to 0, not included, because 0 is not included. However, when I jump over to this other part, as I move to the right, which way am I going? Down. That's right. It's decreasing from 0 into infinity. Okay? Symmetry. You can fold it over that y-axis. So this is y-axis. Symmetry, which means this is an even function. Boundedness. Is it bounded? Well, take a look. Boundedness means, is there a horizontal line that I can draw that the graph never goes past? Well, yeah, obviously, because I have a horizontal asymptote at y equals 0. So it's bounded below. Okay? Is it bounded above? Well, if I draw a line here, it goes through. Anywhere I would draw it, and because it goes to infinity, it's simply bounded below. That's it. Local extrema. Doesn't have any. Because, and you're like, well, Mr. Church, you just told us that if it is increasing and then decreasing, there must be an extrema. Well, it's got to be defined at that point. So there's got to be a hill or a valley that's connected, a hump and a valley. Okay? Well, in this case, it goes to infinity, so there's no maximum value there. It's infinity. Asymptotes, as discussed, x equals 0, right? Check it out. It's where the domain is not defined. So the domain is not defined at 0, so I've got to have an asymptote there. But also, I did my Bobo, Betsy, Bo2 breakdown, and y equals 0 has to be 1, because I've got the bigger exponent on bottom. I'm going to write a similar statement to this. I have to talk about both end. The end behavior is those arrows at the end of the graph, they go somewhere. Where do they go? Well, the limit as x goes to infinity, and the limit as x goes to negative infinity of 1 over x squared, 1 over x squared. Look, where's it going? This is the right side. This is the left side. Where are they going? Where's my right side going as x goes to infinity? Shh, it's going to 0. My left side's also going to 0. Okay, check it out. And this one was going to infinity. Here it's getting closer and closer and closer to 0, but it will never get there. Left side, closer and closer and closer to 0, but never get there. All right. So the next part is a monomial function. Looks like this. A variation of a power function. F of x is equal to k, so that would be k times x to the 0 power, right? Or f of x is equal to k times x to the n. N is positive. Okay, so k is a constant, n is positive. So this is the case that only the positive powers are monomial functions. And so there's only two things that could happen. So either, so n is a positive, but it's also an integer. We're looking specifically at that case. So n is a positive integer. So there's only two things that could happen. X to the n, where n is 1, 2, 3, 4, 5, 6, 7, can only be x is 1, 3, 5, 7, 9, 11, 13, or x to the n is x squared, x to the 2, x to the 4, x 6, x to the 8, x 10. I want to look at this. Check it out. Here's a whole crew of even functions here. Check it out. So I did x squared. Well, that's a parabola. You expect it. But look at how these functions relate to one another. If I turn on x to the 4th, look at that. It was x squared. X to the 4th is skinnier. Does that surprise you? X to the 6th, even skinnier. X to the 8th, even skinnier. What if I added like an x to the 100th power? Look at how skinny that purple one is, right? Okay, so as I move in, my red is x squared. As I increase the power of even, skinnier, 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 skinnier. Okay, the bottom is wider, but the top is skinnier. The end behavior is what I'm looking at. Well, what does that tell us? Check this out. Look at what you notice. What's the symmetry on every single one of these? You can fold them over that y-axis. Well, when I can fold it over the y-axis, okay, I've got these graphs. They go like this. This is my attempt to make them skinnier than one another. They don't actually do that. But if it's even, it has y-axis symmetry. Higher power. Why is that? Well, think about it for a second. They're all going to go through 1, 1 because 1 to any power is 1. But as I get up into these other values, like say for example, what would be 2? So 2, if it was x squared, it'd be 2 comma 4. If it was x to the 4th, it'd be 2 comma and then 2 to the 4th. So 2 times 2 is 4, times 2 is 8, times 2 is 16. Okay? So it's going to go through 1, 1, but then it's going to get skinnier because it has to. Because my values of my y's increase so much more as I increase that power. Let's look at odd values. I've got another collection. I'm turning all these off. Odd functions. Check them out. Here's x cubed. Origin symmetry, right? If I turn on x to the 5th, look at what happens. That red one is skinnier, right? X to the 7th, even skinnier. X to the 9th, even skinnier. What if I did x to the 101st? Check that out. Decimals can't even do it, right? Looks kind of square. But check it out. It's even skinnier. Why is that? Well, it's the same principle that we had with our x squared. As I go and draw my graph, every subsequent value is going to be skinnier, okay? And these have origin symmetry. They're odd functions, okay? And they're skinnier and skinnier and skinnier. And so what can we do with this? Well, they want us to sketch these graphs. They want us to be able to talk about how does it compare with the original. Well, this is what we've been doing, right? You put a constant out front, it stretches it. You increase the power, it stretches it. You put a negative out front, it flips it over. And so if I'm sketching graphs, all I'm doing is throwing these bad boys into my calculator, sketching a graph. So this one is 2x cubed, and it's significant probably to compare it to x cubed, right? Check this out. Notice, my orange is my x cubed. If I zoom out a little bit, watch. My 2 vertically stretches it. And so it's going to be skinnier. So instead of being like this, it's going to get stretched out. That doesn't surprise me. This power's odd. So it's got origin symmetry. Not a problem. What about this one? I suspect it's going to be a flipped version of an x to the 4th. So let's just guess. If this is where an x to the 4th would be, right? Because we kind of looked at that up top. And if it's going to be 2/3 stretched, it's going to be a little bit wider. And if it's negative, it's going to be flipped over. So I'm suspecting that this is going to be a downward opening parabola that's wider than the x squared function. Let's try it. So I'll put this in parentheses. Negative 2/3. Oops. X raised to the 4th power. Check it out. Downward opening parabola. Here it is compared to negative x squared. So the green one ends up skinnier on the bottom and it's flipped over. We've got this downward opening parabola. So were we correct? Absolutely we were. All right, so when we go on to this next piece, it's important for us to understand how these things all relate to one another. And I want to show you something interesting that happens. When I graph y equals x, it's going to look like this. It's that diagonal line. Okay, so I graph this one. It goes through the point 1, 1. If I graph x squared, it looks like this, right? Goes to the point 1, 1. Goes to the point negative 1, 1. If I graph 1/2 x, right? So that would be, so this is y equals x squared. Just labeling these y equals x. If I graph x to the point 5, that's square root of x, right? So that's going to go through 1, 1. And if I graph the negative 0.5x, that's going to come down this way, and it's also going to go through 1, 1. So let me grab red here. So pretty interestingly, what happens is they all go through 1, 1, and they're related, and they've got this delightful symmetry. And if I graphed one of them, 1 through 4 with a k value of 3, the intersection point would not be 1, 1, but 1, 3, because it would take all of my values of y, spit them out, but then multiply them by 3. That's that vertical stretch of 3. Okay, and so they all intersect at this value of 1, 1. And that's the nature of this power function and these relationships that exist, is all of them are related. They come through these same points. And in the first quadrant, that's what happens. So k is positive. So they're in the first quadrant, and they all look like that. If k was negative, they'd be in the fourth quadrant, and they'd look much the same way. Well, the same thing happens here. And I've got a relationship that exists through the point 1, 1, and it's like this. It's testing my sketching powers. So what are these things? Well, if f of x is equal to k times x to the a power, if k is whatever it is, okay, this is going to be 1 comma k here, right? So in the case that it was 3 up above, or when it was 1, it was 1, 1. When it was 3, it was 1, 3. If it was 5, it's 1, 5. Okay, if it's negative 5, it's 1, negative 5. And so k determines where that intersection point is. If a is less than 0, meaning that 0.5, check it out. So up here when k was 0.5, the green one, this is what it's going to look like. So a is less than 0. Oh no, I'm less than 1. I'm talking about the less than 1. A is less than 1, but greater than 0. That's this one. Okay, A is less than 0 is going to be this one that comes down. That was when I was up here and I had that negative 0.5. So A is less than 1 is this red one that comes down like this. So here's my A is less than 0. My other case is 0 less than A less than 1. That's what I just did. That's the square root, right? So it's between 0 and 1. So it's A to the 1/3, or x to the 1/3, x to the 1/4, cube root, square root, those kinds of things, fourth root. What if A was greater than 1? That's going to be my x squared function, right? So x squared or x to the 4th, they all go through that 1, 1 point. So this is A is greater than 1. And if A is equal to 1, that's going to be k times x, so 3x or 4x or 5x, whatever. So this is A is equal to 1. So only 3 things can happen when x is less than 0. Okay, so f of x is going to be undefined. What am I talking about? I'm talking about my domain now. So check it out. This is all in the first quadrant. So that would mean my domain is from x equals 0 to infinity. Well, I'm talking about what about over here? So this is in this quadrant here. So for example, this square root function here, where 0 is less than a is less than 1, it never exists over here, right? So that it's not going to exist over there for the square root function. But like we saw in that first example for the cube root function, it is going to exist. So if f of x is even, okay, so symmetry respect to the y-axis, right? Then it's going to look like this. It's going to be symmetric. So this is f of x is equal to x squared. So what could happen if x was less than 0? So I've got this part here. You're probably like, I don't know what's going on. I'm talking about this graph right here, where a is greater than 0. So if this was x squared, its counterpart, its part when x is less than 0 would be over here. It would be a mirror image. So if it's a square root, like this one, it doesn't exist. If it's a squared, it's a mirror image. If it's even, that's that squared. But if it's odd, it's symmetry to the origin. And so it's going to look like this. So what am I talking about? I gave you this picture. It's only the first quadrant. If it's an even function, its other part is going to be a mirror image. If it's an odd function, it's going to be in the third quadrant, rotational symmetry, origin symmetry. If it's undefined, then it doesn't exist for x is less than 0. Okay, let's do one example. State the value of the constants k and a. Describe the portion of the curve that lies in quadrant 1 or 4, depending on if k is positive or negative. Determine if f is even, odd, or undefined for x is less than 0. Describe the rest of the curve, if any. Okay, so this is 2 times x to the negative third. So a is less than 0. And so if I look up here, check it out. A is less than 0 looks like this one. And so my intersection point is typically 1, 1, but based on this constant of 2, so k is equal to 2, so it goes to 1, 2. All right, so instead of 1, 1, it's 1, 2. And it's going to go like this, right? Because that's my less than 0 portion. So I need to determine, so let's see, determine the portion that lies in quadrant 1. Boom. Determine if it's even, odd, or neither. So let's do this. F of negative x is equal to 2 times x to the negative third. So that's 2 times negative 1 to the negative third. Oh boy, so this is 2 times 1 over negative 1 cubed. So it's 2 times negative 1 cubed would give me negative 1, so this is negative 1 is negative 2. So f of, so this is going to be, sorry, x. Huh. So negative 2x. So let's see. And this is actually cubed here. This is cubed. So negative 2x cubed. You're probably wondering what I'm doing. So here I am. I'm doing f of negative x, and so I plug negative x in here. Well, it's negative x to a negative third power. That's kind of confusing. So I converted to a fraction where I said, okay, it becomes a positive power on the bottom. So it's 2 times 1 over negative x cubed. And negative x cubed is negative x cubed. So if I compare this to my original, then f of negative x is equal to negative f of x, which means it's odd. And if it's odd, what I just told you is this. If it's odd, it has symmetry to the origin. So the other part is going to be in the third quadrant like this. Okay, so what did I just do? Determine the part that's in the first quadrant using my intersection point and my general graph based on what my exponent is. Then determine if it's odd, even, or neither to determine what does it look like. Let's do one more example. My power is 1.5. So that means that it's greater than 1. So it's looking like this, right? That's what my curve is going to look like. My k is equal to 0.4, but it's negative. So if it went through 1, 1, then that means it's going to go to 1, comma, negative 0.4, right? Because it's multiplied by k. So instead of going through 1, 1 and being like this, it's actually going to go through 1, comma, negative 0.4, and it's going to look like this. Okay? And so k was negative 0.4, which means flip over x. And is it odd, even, or neither? So even versus odd. Let's look. F of negative x is equal to negative 0.4 times negative x to the 1.5 power. How do I do this? Well, take a look. This is negative 0.4, negative x, and if this is 1.5, this is 3 halves, which would make this negative 0.4, and then that's the square root of x cubed, so it would be the square root of negative x cubed. So this is equal to negative 0.4, so the top power goes inside, the bottom power goes outside. And so this is negative 0.4 times square root of negative x cubed. And so no matter what I put in for x, because it's negative x cubed, so it's negative x cubed, it doesn't matter. What's underneath is going to be negative. So you see if I put in a 2, it's negative. If I put a negative 2, it's still going to be negative because it's going to be undefined. Okay? So this is undefined. For x less than 0. Okay, and so if we check that one, negative 0.4x raised to the 1.5, right? Check it out. My graph is in the fourth quadrant, no reflection over the x-axis. Okay, so what do we just do? We examined the trends in power functions. They all go through 1, 1 until you multiply them by the k. Based on the a value, meaning the exponent value, they look different. And so we generally sketch it, generally sketch, adjust our 1, comma k, adjust our point of intersection based on what quadrant it's supposed to be in, and then determine even versus odd to see is it origin symmetry, is it y-axis symmetry, or is it neither. Okay? That's what we're doing, guys, being able to analyze power function graphs. Thanks for watching, and we'll see you next time.